We're going to be looking at transformations of logarithms. These are very similar to the transformations we've done in the past. The same rules apply. If something happens inside of a parentheses, it is a horizontal movement, and it will always have an inverse effect. If something happens outside of a parentheses, it's vertical, and it will have the true effect. If it's adding or subtracting, it will be a shift. If it's multiplying or dividing, it will be a stretch or compression, depending on what the number is. If the number is between 0 and 1, it's a compression. And if the number is outside of 1, it's going to be a stretch. All right, and then when I've got a list here started for you, you can see that I've left off actually, is if we drop a negative sign in front, what we're going to end up with is a vertical reflection. Vertical reflection. So we can look at these, and hopefully you're writing these down as we go, but this is going to fit onto our transformation page, the logarithms will. One thing I want you to notice as we're looking at this is the log base b. This has no effect on any transformation. It's just the family of log that it's going to be in. So don't sit there and worry about that number changing. That number could be anything. We're going to stick with 2 though. We're only going to basically work with 3 logs, the common log, which is log base 10, the natural log, which is the inverse of the Euler's number, the e, and then log base 2. So when we're dealing with these, just keep that in mind, that the log base doesn't mean anything as far as transformations. It's just going to be the steepness of the line. So as we begin to change the aspects around these logs, that's going to do the same transformations that we are going to see. I'm going to start by going down to my graph here and getting an idea of what the parent function, the log base 2, looks like. First of all, logarithms are, remember, the inverse to exponential functions. So an exponential function goes through the ordered pair 0, 1. So a log is always going to go through the ordered pair 1, 0. And then from there, just like the other ones was a tripling effect, this one's going to have a kind of a doubling effect, but it's going to be the y that doubles. The x that doubles every time the y. So whenever I go over to the 1, have to go over to the 2 actually, we will have a 4 ordered pair 2. So you can see the movements happen here. We do have some between those, but they're irrational numbers. 2, 1, is not irrational number, but you see this value doubled. It's just that the doubling is going to be happening to the y's. And then it's going to double 1 to 2, 2 to 4, but you see the x values are moving in regards to the y. And then another one we're always going to see on the doubling family is 8, 3. Ordered pair 8, 3. And then everything beyond that is going to asymptote. The negative sign will be opposite of the b. That's negative 1/2. We'll talk about that in just a moment. And then we'll begin to asymptote towards the y-axis this time, because this is a logarithm. So this is the parent function of our logarithm, log base 2 on x. So everything we do, we're going to build off of this line right here. That is the parent function. Okay, and again, if we were to do log base 3, log base 4, log base 5, all it's going to change is the bend in that value. It's going to get steeper the larger the number gets, and it's going to get wider the closer the number gets to 0. And you cannot have a negative number in the log base, so we won't have to worry about that. So the log base, remember, doesn't have anything to do with the transformations. It has all to do with the shape. First, want to highlight for you something in your notes, and that is your little transformation sheet right here. That is the formula that I have on the left, but it's not completely in line with the transformation I sheet had for you before, Because remember, I used to have H's and K's. This one is C's and D's. It really does not matter. Horses and kangaroos, when we talked about that, it doesn't matter the letter because the letter is generic. But here are some things I want to highlight as well inside of these notes, and I want you to highlight as I do. First of all, the B value must be a value greater than 0. And the B value can't be 1. And the reason why the V value can't be 1 is because nothing happens if it's 1. It's basically like saying 1 to a power of anything, because 1 to the power of anything is going to be 1. All right, and then here's the key point I want you to recognize. On f of x log base b of x, you can always plot the point 1 over whatever that b value is and -1. So in our case, that ordered pair, the base is 2, so the ordered pair is 1/2, because the base is 2, remember, as we're working through these, the base is 2, so 1/2 -1. That will always be an ordered pair on these, and the reason for that is because if we have 2 to the -1 power, remember that means inverse, which is 1 over 2. That's why that is. You don't have to necessarily remember that, but that's just the reasoning behind it. Another ordered pair you're always going to see, pre-transformations of course, is the ordered pair 1, 0. And the reason for that is anything to the 0 power is 1, and logarithms are the inverse of that. And then the last one, you'll always have whatever the base is and 1 for the same reason. Exponentials, anything to the 1 power stays the same. Well, the log base logarithms are the inverse of that. So we will always have these 3 ordered pairs. These are the 3 that we can kind of base that on. And you could look down at my graph and get verification of all that stuff. We had 1/2 -1, there it is. We had the ordered pair 1, 0, and then we had the ordered pair, whatever the base is, whatever the base is, in this case the base is 2, and 1. So we do see the ordered pair 2, 1. And since the log base was 2, our y values doubled. See, 2 to 4, 4 to 8. If it was triple, you would just triple the x values. I said y's again, but the x values will triple every time the y's go up 1. Okay, so let's just take a look at these things, and we'll try to sketch these. We'll try to do them in different colors as well. Let me get rid of these couple of things here. So there's our parent function. So when we drop a 3 in front, when we drop a 3 in front of a function, like we have here, this is always going to be our vertical, because it's outside of a parentheses, and it is, in this case, a stretch. It is a vertical stretch, because all the y values are now going to be 3 times what they were. Now, while you get used to logarithms, you're more than welcome to put these in a calculator and see how they happen, but this is what's going to happen on this. The value is going to triple, so all of the values are going to triple. This value of 1 will now be at 3. This value at 2, which was at 1, whoops, did that wrong, sorry. When you triple a 0, it's still 0. When you triple a 1, it becomes 3. When you triple a 2, it becomes 6. When you triple a 3, it's off the graph. But you can see how this has vertically stretched. Same thing here. When you triple a, when you triple a -1, it's now -3. So you can see that this has been stretched, still going through the 1. It's been stretched to triple. So that's what our first transformation would be. Next thing we look at, and you can see this is building off the previous one, we have inside of the parentheses. Well, inside of the parentheses, remember, is horizontal. And since it's a plus sign, that is a horizontal shift. And then you got to fight that urge to want to go right here because if it's a plus sign. But remember, there's always inverse behaviors inside of those parentheses. So we are going to go left 4. Every one of these points will now be moved left 4 units. So the one that was at 4, 6 is now going to be moved over 1, 2, 3, 4, and it's going to be sitting here. The value that was at 2, 3, moving over 4 units, 1, 2, 3, 4, will now be sitting here. The value here is now sitting 1, 2, 3, 4. And then our asymptote, which used to be at the origin, is now at -4 because we shifted this thing 4 units to the left. So you can see it's the same shape as our red function, just shifted over 4 units. The next transformation they're throwing at us is a -2. Outside of a parentheses means vertical. Adding or subtracting makes it a shift. So each and every point is going to go down 2. So this point that was now at 0, 6 is now at 4 because it went down 2. This value will go down 2. This value will go down 2. Our asymptote will still be at -4. It's just going to be like that. Graph's not perfect there, but that's where I would probably go and look at the table and see what I got. So our transformations, you can see we started with the black one here. We stretched it vertically, so it's like taking a piece of rebar and bending that up 3 times as fast. And then we shifted it left 3 units, and then we moved it down 2 units. So this is our transformations of logarithms. Hopefully that seems very familiar. All I want you to put on D is the fact that these two are identical functions here. We have not talked about log properties yet. This is inside of a parenthesis, so this would actually, you can write this down, I guess, would be a horizontal. It's actually a compression, even though it feels like, well, that number 8 is not between 0 and 1, but remember we deal with the inverse. So this would be a horizontal compression by a factor of not 8, but the inverse, 1/8. All right, now let's take a look at E here. Taking a look at E, it's the tripling function, which is the red one, but we have a negative sign in front, which is a vertical reflection. And basically put, a vertical reflection, all the y values will be opposite. So we have the value, this one would be the same because it's vertically reflected, it's the same thing. But this value that we had at 2, 3 will now be at 2, -3, which is down here. This value that we had at 4, 6 will now be at 4, -6. Everything else went off the graph there. This value we had at 1/2 -1 will now be at 1/2 +1. And this thing will begin to asymptote as it reaches positive infinity instead of negative. And that's what we talked about, our vertical reflection. Little math tip here is what we highlighted from the things. Remember those ordered pairs that you're looking for. And guys, I will just be honest with you, you're probably going to forget them numerous times. Use the graphing calculator and look these values up. The problem with logarithms is a lot of times the logarithms are irrational numbers. So it's oftentimes very hard to find values that are easy to graph. So there's a lot of estimations, so things can be off just a touch. So you can see I've got a copy of our Desmos graph of this this function and the ordered pairs that we should be seeing when we look back up at this thing, and we see 0, 4, we see, well, 4, 7's off the graph, but that's what we would have seen. We see -2, 1, and -3, -2. So as we look at that, what we going to learn here is that our transformations are correct. And then we can see all of those things, how the function has been affected by those. Now we'll take a look at the last two. Like I said, the number of logs there are is infinite. But we're going to stick to three basic ones. The log base 2, which we just finished. Common log, which is an understood 10, by the way. And then the natural log, which is the inverse to our natural base. We're not going to graph these just because we don't have space. If you want to, you're welcome to go over to your side and do that. What we're going to do is just identify what we see. I actually feel like these two are probably easier just because we don't have other numbers in the way. But this is our log base 10, which is called the common log. A lot of people get confused between common and natural log. Remember, the n goes in this spot here. Before you ask the question, why isn't it NL, you can do your own research on that one, but it is not log natural, it's a natural log. All right, so here we have the common log. Again, common log, if you were to put this in your calculator, by the way, it would calculate it correctly because that is the same thing. And the reason why it's called a common log is because of scientific notation. Because you remember on scientific notation, we do 2.3 times 10 to the 12th power. And the way you get rid of that 10 base is with a common log. That's just the log. So it kind of warrants its own button on your calculator for sure, because that's usually the one you're going to do, especially scientifically. Okay, so this is a log base 10, so this is going to be definitely different shape than the log base 2, which will make it lay closer to the x-axis because it's going to grow at a much faster rate. But that's not what we're talking about here. What we're worried about here is the transformation. So on our AI, what we have here is the change in the A value, but it's a negative sign. So this is going to be a vertical reflection. You guys try to work ahead of me on these and see if you can determine what's about to happen on these. So the 2 in front. Since it's in front, like I said, and not in a parentheses, that makes it vertical. Since it is not adding or subtracting, that makes it a stretch or a compression. And in this case, the number is not inside of 0 and 1, so it is a vertical stretch by a factor of 2. Next one is inside of a parentheses, which makes it horizontal. It is adding or subtracting, which makes it a shift. And remember, everything has an inverse behavior, so this is going to make us go left 1 unit. On example 4 here, there are actually 4 transformations. Think about that for a second. There are 4 transformations. We're going to write this one over to the left side where we can get some room. Think about what those 4 transformations are. If you're seeing 3 and wondering what the 4th one is, you're not doing too bad, but you're forgetting something, and that's the reflection. So on I, let's take care of the easy things first, the shifts. We have a horizontal shift, and we have a vertical shift. Because we have a plus or minus sign, we know this is to be true. So we have our horizontal and vertical shift. Think about what that would be. Horizontal is the one inside of the parentheses, so this one will be going right 2 units. And the vertical shift is outside, which is the 1, so this is going to go down 1 unit. Excuse me. Up 1 unit. Got my mind stuck on the horizontal, so this is going to go up 1 unit. We have multiplication on the outside, which makes it vertical. It is a stretch because that number is outside of 0 or 1. So it's a stretch by a factor of 3. Notice I did not say negative 3. And then by not saying -3. I'm sure some of you that were stuck on, well, what's the fourth one? Hopefully now you recognize that that is the vertical reflection, which was caused by the negative sign that is put in front of the 3. Let's move to option number 5 here. This one can be confusing to people. You don't see a parentheses, even though that x looks like the 3 looks like it's attached to the x. If there are no parentheses, that makes it vertical. So it is a vertical shift. Without the parentheses attaching the x to the number, it's going to be a vertical shift. We're going to go down 3. And then the last one is in front of it. It is multiplication. So that makes it, in this case, a compression. Think of why it's a compression as opposed to a stretch. And it's a compression by a factor of 1/2 because the number is between 0 and 1. All right, so let's move on to the natural logs. Again, natural logs are just a different base. The transformations are going to be the same. So this one actually has 3 of its own. VI, that is an I, sorry. Inside the parentheses is our horizontal. Adding or subtracting makes it a shift. Horizontal shift, left 1. The II here. We have 2 things. We have no parentheses, so we have vertical and vertical. Remember, horizontal take place inside of a parentheses. Let's take care of the easy one. This is a vertical shift because it's an adding or subtracting sign, and it is going to go up 1 unit. And then we have a vertical stretch because the number is not between 0 and 1. Vertical stretch by a factor of 2. We'll do the II right here. We've got our vertical stretch again, and that's because of the 3, and that 3 is not between 0 and 1, so it's a vertical stretch by a factor of 3. And then we have, secondly, a horizontal shift. Inverse, think inverse when you have horizontal. As much as you want to make that go left, it's actually going to go right 1 unit. And then lastly, the fourth option here, 2 movements, both vertical. One of them I think we all should have by now. It's a vertical shift down 2, because that is the value that's just simply added to the end. And then we also have a vertical reflection. And just remember this, if you don't see vertical reflection, this is also known as a reflection across the x-axis. And I think on C we're just going to move past this one. You have your notes. If you wrote your notes, just put C notes on previous page. Because what the information they're looking for is that the A stretches, the C shifts vertically, vertical shift, and the D stretches. I said vertically, I wrote horizontally. It is horizontal, and this is a vertical shift. You don't need to rewrite all that stuff anymore. You're good. All right? It says, looking and making structure. Compare the effects of A on a logarithmic function on a log B of x to the A on a squared. Well, think about what the logarithm did. If you think about the logarithm, when we put the A value in, the parent function looked a little something like this. And then when we added a value that was outside of 0, it's almost like a magnet was pulling it close to this y-axis up here. It went here and it got pulled. It's like the rebar, like I said, is pulling it towards this y-axis. Well, when we think back to our parabolas, it actually had the same behavior, where this might have been the parent function of a parabola. When we added the slope, it's like that magnet kicked in on the y-axis. So if we put a 3 in front of that, it got closer and closer to that magnet. So it says assuming A is positive, of course, but this is too broad of a question, because what if the A value is a fraction? Well, if the A value is a fraction, it's almost like the magnet is coming from here. And it's almost like the magnet is coming from here. So really there's 5 different behaviors that this could be happening, but I want you guys to make the connection here. It says compare the effects. I mean, they're the same in the rate of change. If I guess we could put something about that. The rate of change is the same. And then compare the effects of C. These both shift horizontally. And I'm hoping that we are all really good at these by now. We've done a lot of transformations. Hopefully you guys have gotten these things figured out. There's actually more sections to come. But if you keep getting these things where it's like, hey, inside the parentheses, outside the parentheses, if you continue to learn these things and master these, it's just going to get easier and easier, because all we're going to do is change the signs around the transformations. You had these for trigs, you have these for radicals. Rationals are kind of a different story, but we'll talk about that when we get to those. And we don't even actually have to cover those, but we will talk about them. All right, that is that. What I would like for you to do is to finish out our last little sections here, the lesson 23.3, and you will have to look back to the A section on these to talk about what we're learning here, which is the effects on domain and range. As far as the graphing goes on these, graph these functions, that's for your own benefit. If you can't attach a graph easily, that's fine, but I do want the written description of these transformations. And don't worry about squeezing it in. If you need to attach it to another sheet of paper and screenshot it or whatever you need to do, just get those to me.